Okay, so we are going to continue our discussion on minerals and specifically where we left off on rock forming minerals. So we have several different types of rock forming minerals, but they can be really separated into two different groups, silicates and non-silicates, with several sub sections of non-silicates that will go over the major ones that we can see. Silicates are our main type of rock forming minerals. They make up over 95% of the different minerals we see on our crust. So if you remember back to the chemical compositions of the Earth and broke down into different sections, you'll remember that as a whole, silicon and oxygen are the two most common in the crust, with them being major components of the rest of the Earth's composition, but not including iron, some magnesium too. So there's other elements, but the silicon and oxygen are the most common. So in silicates, what they are a combination, or the building blocks of the minerals are silicon and oxygen, and typically they're in this form of a silicate tetrahedral, where there are 4 oxygen atoms with one smaller silicon atom. And they form these tetrahedrals, and that makes their shape. So, if you notice, we've got our SiO4 is that building block of what the silicate minerals are. So they can form in different structures. Our main structures are our single chain, then we have double chains, sheet silicates, and framework silicates. And depending on the structure will greatly influence the strength, the cleavage planes, and other features that we can see out of our minerals. So let's look at a couple of different these. So if we're looking at our single chains, we have cleavage planes of two planes at 90 degrees, with not a super complex formula. Our common one here is pyroxene, which has a chemical composition of magnesium, iron, and then the silicon, and 3 oxygens, not the 4. Olivines are a isolated tetrahedral, so instead of a system where these are organized, this is an unorganized set of tetrahedrals, and this would have MgFe2SiO4 and has only one plane of cleavage. This olivine is typically a more mantle-oriented mineral, found mostly in peridotite and sometimes can get into basalts, but it is more of a mantle mineral. We also can get amphiboles, which would be our double chains. And so what happens here is they get organized in such a way that this affects their cleavage planes, and so pushing them towards each other and putting them into this double chain system causes them to have 2 different planes of cleavage, but they're at 60 and 120 degrees, not at 90, because you are forcing these tetrahedrals closer together. And you also can get a more complicated chemical formula. Muscovites, or sheet silicates, those typically have a single plane of cleavage. They are planar, so if you remember to lab, we have muscovite micas and biotite micas. These can get extremely complex in their chemical formula because they are in this sheet orientation. So if you remember back to the cations and anions of different sizes, because this is in a sheet system, then those larger cations and anions can get into this structure and allow for these larger cations and anions. And they just organize in single sheets. And then we have 3-dimensional framework silicates. And these have 2 planes at 90 degrees and are felspars. So these are really our building blocks of more complicated rock systems like our igneous rocks that help form in these, and these are really the basis of them. All right, so let's look at the formation of these guys. So our silicates are one silicon atom for 4 oxygen atoms, and so they form in this tetrahedra with the silica at the center and the 4 oxygens around them. And so then if we start looking into a quartz structure, which has a chemical formula of SiO4, then we can start seeing how they, or SiO2, I'm sorry. Quartz has a chemical formula of SiO2. And so these are starting to collate and organize as these tetrahedrals. So these are pretty much the basics, as I've said earlier. For our non-silicate minerals and non-silicate based rocks, we see several different mineral forms. So first off, we'll start with carbonates. Carbonates are ones that we see quite a bit as marine scientists and marine geologists because they form a lot by organisms that are secreting a calcium carbonate system or solution that then hardens and becomes shells or bones or reefs. So what is happening is we have several different cations, a lot of times calcium, but can also be magnesium and iron, bonded to carbonate, which is CO3 with a negative 2. So our most common of this is CaCO3, which is a calcium carbonate, which is a lot of what reefs are. So we see these a lot. We can also see sulfides, where we see, again, calcium and iron and sometimes strontium bonded to sulfur or sulfates in this system, and oxides as well. We also, a lot of commons one we see as marine geologists and marine scientists are evaporites. So one of these is sulfates, which is a something like gypsum, where these have a large component of water to them. And so with gypsum being calcium sulfides and 2 water molecules. And these are formed through the evaporation of water, and then the minerals and heavier elements are left falling out of solution and form these minerals. And halides is another one of these, where we have positive ions attached to negative ions. So our example of this is halite. And so again, this is very similar, where this is a salt, and when water is evaporating, this can get left behind because it can concentrate in solution if ocean water gets isolated and doesn't get to mix or move through a system or get flushed out, and it is in a system that is hot, that water can evaporate, leaving behind the salt. So we get halides. All right, so let's look at a couple of different ways that minerals form. So ultimately, we have atoms coming together in proper proportion and proper alignment, forming a unique structure or a defined structure in that chemical properties. So when they form, they can form through cooling of molten rock. And so like a lot of this and a lot of these minerals are just they are falling out of a solution. So you have some form of fluid, whether it's molten rock or water, that cools or heats up, so evaporation of water, that water leaves, or cooling a molten rock, and so certain minerals are going to fall out of solution in a very particular order. And then we can also have changes of temperature and pressure on an existing mineral. So just like we talked about with graphite and diamonds, where you had a change in pressure and temperature and reorganizing the crystalline structure of graphite can make it become diamonds. All right, so in this, I will allow you all to continue on, or encourage you to continue on looking at the presentation. There is a movie embedded in this, talking about the Nicaea crystal caves. So for the rest of the assignment and for this portion, please go through there's a video that describes what Nicaea cave is, and these really large gypsum crystals and how they formed. And so I will encourage you to do that. Now, remember, I am posting a Moodle quiz about minerals for this too. So you'll have a couple of days to do that, but please check Moodle. All right. We will continue on with the next lecture. Okay, thank you. Bye.